In a simulated environment, modern computer vision algorithms are remarkably precise. When trained to identify a diseased leaf, a well-optimized model can consistently achieve a 94% mean average precision, perfectly framing the target frame after frame. But transfer that exact same algorithm onto a physical robotic chassis moving through a field, and that 94% precision often yields a complete miss. The software identifies the leaf perfectly, yet the physical nozzle hits nothing but empty air trailing behind the target. The breakdown here does not lie in the vision algorithm's accuracy. The system is failing because it ignores the rigid physics of the system's latency budget. We can define this latency budget as a physical measurement of time. It is the total accumulated delay from the exact millisecond light enters the camera lens to the exact millisecond liquid physically exits the spray nozzle. To engineer effective precision agriculture, we have to deconstruct this perception-to-spray pipeline step by step. We need to measure exactly how time translates into mechanical displacement. When temporal delays and physical constraints are ignored, relying on a simple open-loop controller, one that simply shoots when it sees a target, becomes functionally useless for millimeter-precise agricultural tasks. The constraints of this latency budget are forced by the physical environment itself. In Chinese solar greenhouses, operations are strictly limited by narrow row spacings that span only 40 to 80 centimeters. That confined geometry entirely precludes the turning radii required by standard wheeled robots. Developers are forced to rely on heavy rail-mounted platforms or highly specialized narrow chassis designs. Inside those narrow rows, the robots face a second, more destructive constraint, a persistent relative humidity hovering between 80 and 95%. This continuous moisture actively degrades standard commercial electronics. Without specialized protection, the mean time between failures for edge computing hardware drops to under 200 hours. Engineers have to hermetically seal the electronics. Between these heavy enclosures and the constraints of a rail chassis, there is a hard limit on the mass, power draw, and cooling capacity available for the hardware processing the algorithms. A physical AI deployed in a greenhouse must first survive the greenhouse. The heavy thermal and power restrictions leave the robot's brain with a heavily restricted compute capacity to process incoming data. To maintain economic viability in a large facility greenhouse, the inspection robot needs to maintain a constant baseline velocity of 0.3 meters per second. This timeline tracks step 1 of our latency budget, camera perception. Above, the chassis moves along its x-axis at 0.3 meters per second. Capturing raw light data takes 30 to 50 milliseconds. In that window, the robot drifts forward. Next is step 2, edge inference. Processing that image and drawing a bounding box around a disease cluster on low-power edge hardware takes 50 to 140 milliseconds. This requires a lightweight YOLO architecture, operating at 10 to 20 frames per second. Theoretical benchmarks often favor transformer-based models like VIT for their multimodal fusion capabilities. However, on edge hardware like the Jetson Xavier NX, their frame rate collapses to between 2 and 5 frames per second. That heavy architecture incurs an algorithmic delay ranging from 200 to 500 milliseconds. During a 500 millisecond delay, a robot traveling at 0.3 meters per second will move 15 centimeters blindly before the AI even registers a valid target. That margin of drift makes lightweight YOLO architectures a hard physical requirement for mobile spraying, even though they struggle more with cross-crop generalization.
Algorithm selection in precision robotics is dictated entirely by these edge compute latency constraints. High map scores mean nothing if the inference speed lets the target slip past the chassis. Once the AI finishes thinking, the digital signal still has to trigger a mechanical action. This initiates the decision delay. This cross-section shows the controller processing the bounding box into a targeting matrix. Translating that data into an electrical pulse takes 5 to 10 milliseconds. Then we hit the actuation delay, the time required to physically trigger the PWM solenoid valves. Because we are dealing with the physics of moving metal, forcing the mechanical components of the PWM valves to slide open adds a mandatory 10 to 20 milliseconds to our budget. Finally, the system faces the fluid dynamics delay. Building an operating pressure of 0.2 to 0.6 megapascals and breaking that liquid into a precise 100 to 300 micrometer droplet spectrum consumes a final 5 to 15 milliseconds.
The fastest software commands in the world will always pay this temporal toll to mechanical and fluid physics before work is actually done. We can now tally the exact toll: 50 milliseconds for perception, 140 for inference, 10 for the controller's decision, 20 for valve actuation, and 15 for fluid dynamics. The cumulative latency budget sits between 100 and 235 milliseconds of total delay from light hitting the camera lens to liquid hitting the air. This calculation shows the kinetic reality of the system. We multiply the maximum latency of 235 milliseconds by the robot's baseline velocity of 0.3 meters per second. The result is a physical displacement of 3.0 to 7.1 centimeters. That is the distance between the exact coordinate where the AI saw the target and the coordinate where the nozzle actually sprayed. An open-loop controller operates by triggering the nozzle at the exact moment the target is centered in the camera frame. When applying highly concentrated variable rate pesticides to specific millimeter-scale disease clusters, a 7-centimeter miss is catastrophic. It wastes chemical inputs and leaves the pathogen untreated. Open-loop controllers inherently fail in mobile robotics. They execute actions based on spatial data that is already stale by the time the mechanics fully activate. The engineering solution to this displacement is software-defined closed-loop latency compensation. This schematic demonstrates how a closed-loop system dynamically calculates its own latency budget in real time, constantly pulling the chassis velocity sensors to project a vector ahead of the robot. By treating the 235 millisecond delay as a deliberate lead time, the predictive targeting system fires the PWM solenoids before the target aligns with the nozzle. The leaf and the chemical cone arrive at the same coordinate simultaneously. The obvious alternative is to simply buy faster edge compute hardware, driving the latency budget down near zero so predictive targeting isn't necessary. But the economics of agriculture prevent that. Current commercial integrated systems cost between 180,000 and 250,000 Chinese yuan per unit. The actual capital budget for medium-sized facility greenhouses enforces a strict equipment cap of 50,000 to 80,000 yuan per unit. Throwing raw, expensive compute power at the problem violates the core business model of facility agriculture. The hardware must remain cheap, which means the software must remain highly disciplined. True physical AI requires algorithms that respect both severe economic constraints and the physics of time. It demands precise calculations for the exact moment bits must become mechanical action.